So I'm gonna now hand the floor to Joel. Joel, please.
Okay, thank you very much. Well, it's fun to be here in Boulder. I had such a great time giving the Reinhardt lecture yesterday. That was really a lot of fun. Today I want to tell you about modal theory. And let's see, do I just click down? Is that going to work? No.
The arrow keys. Try the arrow keys to the right.
I did, but it says stop summary. Let's see. Oh, there we go. Okay. So this is joint work with a student of mine, Wojciech Woloshin, in Oxford. And the paper appeared last year, and he's continuing further work on this currently. So I think all of the theorems, almost all of the theorems, are joint with Wojciech. Some of them are appearing only in his dissertation. Okay, so right, in modal theory, we consider a mathematical structure within a class of similar structures. So we're going to not just look at one group or one graph or one field. We think about it in a context with a lot of those kind of structures. If you want to think in terms of category theory, that's totally fine. So a potentialist system for us is a class of models with an extension relation. So we have a way of going from any one of those structures to a larger one, and that original structure is somehow going to be inserted inside the larger one. And then we define the modal operators in any such kind of context. So we say that one of those models, and maybe it's a graph, maybe we're doing graph theory, modal graph theory, or maybe it's a group, or maybe it's a model of piano arithmetic, or whatever it is. In the context of that potentialist system, m thinks phi is possible, written with this possibility operator. So possible phi means phi is true in some bigger model. Okay, so the smaller model thinks phi is possible if you can make it true in a bigger model. And it's necessary, phi is necessary if no matter how you make it bigger, phi is true. Okay, so those are that's just standard Kripke definition of the modal operators in such a system. So this potentialist system is just a gigantic Kripke model, and we've defined the normal modal operators for that context. Okay, so a principal case that I'm interested in is when I have a first order theory T, like graph theory or group theory or algebraically closed fields or whatever your first order theory is. And we're going to look at the class of all models of that theory, and we're going to do modal theory with respect to that theory. Okay, all graphs, all groups, all fields. Those are all special cases, but actually we've done quite a lot of work looking at models of PA in this case, and also models of set theory, where it interacts with sort of potentialist views in the philosophy of mathematics. Today I'm going to concentrate on these earlier ones. Okay, so every graph, a graph is just a bunch of dots with an edge relation between the dots, the adjacency relation. I claim every graph thinks possibly the diameter is 2. If you have any graph at all, maybe it has an infinite diameter. The diameter is diameter 2 means that any 2 points are connected either directly or with one intermediate point so that you can get there in 2 steps, right? But possibly that's true because if whatever graph you have, I can add another node that's connected to everybody, and now it has diameter 2 at most. Okay, so every graph thinks possibly the diameter is 2. Every group is possibly necessarily non-abelian, because even if it was abelian already, I can make it bigger into a non-abelian group by taking a direct sum with a non-abelian group or whatever. That's going to be a bigger group, which is non-abelian. And once it's non-abelian, then it's necessarily non-abelian, because in all larger groups, it will be non-abelian. Every field thinks possibly every element has a square root, because if I have a field, I can go to a field extension where I've added square roots of all of the elements. And so it's possible that everybody has a square root, but it's not necessarily possible. It's not necessary, because I can also go to a transcendental extension where I don't have I have an element without a square root. And so just because everybody has a square root now doesn't mean that it's necessary that everybody has a square root. Okay, so I hope this is helping to explain this kind of modal language. We have many languages in this context. So there's the original language L, that's the language of the theory T, the first order language. Then we have the language that we call Diamond L, which is a partial modal language. We just close L under Boolean combinations and the modal operators, but not under quantifiers. Okay, so in this language, the modal operators never appear under the scope of a quantifier. But the full modal language, L diamond, is where you close under everything. So in this language, you can have modal operators appearing under the scope of a quantifier. But then we also have this actuality operator, which I'll explain. It's a richer modal language with actuality, allowing you to refer to the actual world. You want to say possibly something such that actually something, referring back to the original actual world. And then P is propositional modal logic. This is just a language that has propositional atoms and Boolean operations and modal operators. So for example, everything in in diamond L is a substitution instance of one of these guys. Every statement here is making an assertion about some propositional variables. And if I substitute L assertions in for those variables, then I get a statement of this form, and that's going to be in diamond L always, because none of these things will ever have, there's no quantifiers in this P because it's in propositional modal logic, and therefore none of the modal operators will appear under the scope of a quantifier after you do that substitution. Okay, so we have to be straight about these languages. So the language of modal graph theory has remarkable expressive power. I want to convince you of this. Two-colorability is expressible in modal graph theory. So I'm talking about vertex colorings with two colors so that adjacent vertices have different colors. That's what I mean by a two-coloring. This is definitely not expressible in graph theory, in the first order language of graph theory, because if I have, say, an odd cycle, that's not too colorable, because if I go, blue, green, blue, green, blue, green all the way around, because if it's an odd cycle, then I'm going to need a third color to make a coloring of an odd cycle. But then if I take an ultra power of all the odd cycles, that's going to be a graph, and every node is going to have order 2, degree 2, because that's true in all of the odd cycles. But there won't be any finite cycles because, once the finite graphs get big enough, it's going to concentrate where there aren't cycles of that. So the ultra product is just going to be a bunch of Z chains, which definitely is too colorable, even though none of the ones in the ultra product were too colorable. So therefore, it can't be expressible in the first order theory, but it is expressible in modal graph theory. So if you have a graph G, then I think G is too colorable just in case, possibly, which means in some bigger graph, there are adjacent nodes R and B, for red and blue, such that every node is adjacent to exactly one of them, and adjacent nodes are connected oppositely to them. So basically, R is connected to the ones that you want to think of as being red, and B is connected to the ones that you want to think of as being blue. And so if I have two nodes R and B like that, so that everybody's connected to one of them, but adjacent nodes are connected to them oppositely, then that defines a two coloring on the original graph. So if it's too colorable, I can put two nodes in like that point out the coloring. And if I have two nodes like this, then it determines the coloring on the whole graph. In fact, it's a little paradoxical because R would actually get colored B because it's connected to B and not to R, and B would get colored red because it's connected to R. So you have to keep it straight. But okay, so two colorability is expressible. Connectivity is expressible in modal graph theory. It's definitely not expressible in the first order theory to be connected, because if it were, then I could write on a theory that says A is connected to B, but not in one step, also not in two steps, not in three steps, and so on. So that theory is finitely consistent, therefore satisfiable, but it wouldn't make sense because they would be connected, but they wouldn't have any distance between them. Okay, so therefore it's not expressible in ordinary graph theory, but it is expressible in modal graph theory, because I can say X is connected to Y in the graph by a path. That's what I mean by connected. If and only if necessarily, that means in all larger graphs, whenever you have a point C that's connected to X, that's adjacent to X, and also its neighbors are closed under adjacency, then it's also adjacent to Y. So what I'm saying is, if X is connected to Y, if and only if whenever in any bigger graph you have a point that's adjacent to X, and the neighbors of this point are closed under adjacency amongst the other points, then it's connected to Y. Because if X and Y were in different components, then I could just add a C that was connected only to the X component and not to Y. And it would satisfy the hypothesis but not the conclusion. So, but if it is connected, then of course by induction on the length of the path, you can see it's going to have to be connected to Y. Okay. So that's the expression in the modal language is a modal operator necessarily for every C, if C is connected to X. And whenever I have U and V, so that C is connected to U and U is connected to V, which is not C, then C is connected to V. That's the closed under neighbors part. Then C is connected to Y. So that's exactly expressing what we said. Okay, finiteness is expressible in modal graph theory, which is definitely not expressible in any first order language because of compactness. So G is finite if and only if possibly there's a node N whose neighbor graph is connected. We can express connectivity, whose neighbor graph is connected, and every point there is degree 2, except for 2 vertices of degree 1, a beginning and an end, and all other nodes are adjacent to distinct nodes. So what I mean is, okay, you're living in some graph G. I claim it's finite if and only if possibly there's a node whose neighbors all have degree 2 except for a beginning and an end and are connected. So it's going to be a finite chain such that everybody's connected to a unique neighbor of that node. That expresses finiteness. In the paper, we write it out, but I thought it's so complicated, so I'm not going to write out the formula. But obviously, I'm just using modal graph theory concepts here.
There exists N. Is that there exists N up there?
It's a node, not a finite number. It's a
Oh,
node.
all right, okay.
It's representing a finite
All
number.
right, okay. I was.
Yeah, I'm sorry. It's a vertex. There's a vertex, and that's what I mean there. I'm not quantifying over the natural numbers. Okay, accountability is expressible. We just expressed finiteness, but I want to do countability. It's just the same idea, except now I say G is countable if possibly there's a node, which I'm going to call omega. I'm not quantifying over ordinals, whose neighbors have all degree 2 except for one point, which is beginning, and they're connected. And all other nodes are adjacent to distinct neighbors of that node. So it's like this. The point is that omega has the neighbor graph is connected and everybody has degree 2 except for one point, the star. So it's going to be a copy of omega because it's connected. It can't be like omega plus z, that wouldn't be connected. So this connected is doing a lot of work. Such that everybody is connected to a distinct neighbor of omega. So that makes it countable. So countably infinite would just be countable but not finite. We can express size at most continuum because G is a graph with size at most continuum if and only if we can associate every node in the graph with a distinct subset of omega. We can summon into existence this copy of omega because we say possibly there's a node whose neighbors are connected and everybody has degree 2 in that neighbor set except for one point which has degree 1 in that neighbor set, such that everybody is connected to a distinct collection of nodes adjacent to omega. Every point, any 2 distinct points here have to be attached to different subsets. But that's expressible because I just say for every x and y, there's somebody adjacent to omega that's adjacent to x and not y, or adjacent to y and not to x. So the sets that they're connected to are different, but there's only continuum many subsets. So therefore, I'm saying that the graph has size at most continuum if you can do this. You can also express size exactly continuum. It's a little trickier. Okay, you can express size all of 1, size exactly all of 2, all of 3, all of omega, Beth omega, and so on. These are all expressible in modal graph theory. You can say the graph G has size Beths of omega with a modal graph theoretic assertion that's expressible. You can say it has the size of the least Beth fixed point. So this enormous cardinal. It's not a large cardinal, it's a very tiny cardinal. Okay, but it's pretty big though. Okay, the least hyper Beth fixed point, that's a fixed point of fixed points. Okay, and much more. So there's a huge fragment of set theoretic truth is interpretable in modal graph theory. Okay? We don't know yet if we can interpret the set theoretic universe in modal graph theory. We don't know the answer to that yet. We conjecture that it's not possible. If you have the actuality operator, then it is possible. We can prove that. So, but we don't know how to get rid of the actuality operator. Okay, so let's just talk briefly about modal group theory. So this is, of course, a different theory. Now, before we were doing graph theory, now we're doing group theory. So T is group theory, the language of groups. Let's just express some features in modal group theory. So we're looking at all groups under the subgroup relation, the group extension relation. So a group thinks something's possible if there's a bigger group in which it's true. So the relation, this is some newer work in Wojciech's dissertation. The relation that Y is in the group generated by X. So X is generating a cyclic group. Y is in that group. This is, I'm sorry, I said definable, it should say expressible. It's expressible in modal group theory. Okay, it's definitely not expressible in first order group theory, because if it were, you could express that the group is cyclic. But that would violate the Levenheim-Skolem theorem because there's no uncountable cyclic group. So if you could express I'm a cyclic group, there would have to be models of every cardinality, but there are no uncountable models of that theory. So therefore, you cannot express being cyclic in the first order language of group theory, but you can express it here because you just say every Y is in the group. There is an X such that every Y is in the group generated by X. And that would say it's cyclic. Okay, let's express it. So Y is in the group generated by X, if and only if necessarily, that means in all bigger groups, any Z that commutes with X commutes with Y. Of course, if Y is in the group generated by X, and there's some power of X, and so any Z that commutes with the generator is also going to commute with all the powers of it, and therefore it would commute with Y. So that's half the direction. I mean, half the equivalent. But the other direction, what we need to know is that if Y isn't in the group generated by X, then there is some larger group with an element that commutes with X, but not with Y. And that's true because of the Higman-Neumann extension. You can just add a generator that commutes with X and look at the group generated by those relations, the ones that you already had, plus this new thing, and it doesn't commute with Y. And therefore, it gives a group which has an element that commutes with X and not with Y. So that gets the other direction. Okay. Oh, I guess this is a different proof that it's not. You can take the ultra power of Z. Okay, that's going to be an uncountable group, which is not cyclic. Okay, having finite order is expressible in modal group theory, which is definitely not expressible in first order group theory by compactness. So I claim X has finite order if and only if the group generated by X has some other generator other than X and X inverse. Okay, but there's these weird exceptional cases. Or X has one of these orders. Is it if X has some finite order? Okay, if it's one of these, I mean, if X has some finite order other than these, then because there's going to be numbers that are relatively prone to the order other than 1 and -1, we're going to get another generator other than X and X inverse. So that will show that it's that it has finite order. Right. So if it does have finite order, clearly it satisfies this because of that reasoning. And if it satisfies this, then it must have finite order. Because if you have another generator other than X and X inverse, then it has to be a finite cyclic group. Okay. So that's not expressible in the first order language of group theory because we could take an ultra product of the finite cyclic groups. And that's going to be a group. These are all finite order, but in the bigger group, everyone's going to have infinite order, I think, except for the identity. Okay, so being torsion is expressible in modal group theory. So to say everybody has finite order, I mean, if you can express having finite order, then of course you can express being torsion. But that's definitely not expressible in the first order language. Okay, so let's now talk more generally about modal model theory. I want to develop some of the model theory of modal theory. So I'm going to think about the case of mod T. Both of those previous cases were instances of this mod T, either for T equal graph theory or T equal group theory, but you can have any theory that you want. In the class of all models of T, then I'm going to say it's a direct extension if M is a submodel of N. These are both models of T, and it's a submodel. I call that a direct extension. But we might also compare it with another one pretty soon. This relation from a potentialist point of view, if you're a philosopher studying potentialism, then the direct extension is extremely natural because you're living in a universe and you want to imagine that maybe the universe got larger, and so the individuals in the smaller universe are still existing in the bigger universe. They don't have counterparts or something. It's exactly the same individuals that are continuing to exist, even though more objects have been added to the universe. So that's a very natural kind of picture from that potentialist point of view. However, direct extensions have extremely poor algebraic properties. It's not convergent. So convergent means that if I have a world and I go to two different worlds, then I can find a world where they come together. And if you're doing direct extension, then that's almost never true, because if I have a group and I put it inside two other groups, maybe the particular individual I used over here was also used over here in a way that is incompatible with putting them together, because maybe that guy had order 2 over here, but the particular object was used over here in an order 3 way or something, and so there's no way to put them together. Okay, so that means that you're almost never going to have convergence. It's not going to be directed. So the closure properties of the potentialist system are very bad when you use direct extensions. Rather, mathematicians generally prefer the embedded extension idea. So we say, look, if I have an object, then it's fine to just take an isomorphism to a substructure of another one, and that's my extension concept. So the embedded extension concept is far more natural to mathematicians. So philosophers like this one, mathematicians like this one. And the reason they like it is because it often has these much better properties. So for groups, for example, we get amalgamation and so forth that we definitely don't have in the direct extension case. But fortunately, the modal assertions are again. This is one of the things that Wojciech and I proved. It doesn't, as far as the truth of a modal assertion, it doesn't matter which extension concept you use. So therefore, you can be motivated by this kind of picture, but think about this one when you're doing the semantic. Oh, okay. Basically, this just amounts to proving that, like, if something happens in some copy, then you can take different individuals for that thing and it won't affect. So if you have two isomorphic structures in mod T, then they're going to satisfy exactly the same truths. And if you think about that hard enough, it turns into this theorem. Another student of mine in Oxford, Sam Adam Day, proved, in fact, the two potentialist systems with the two different accessibility relations are bisimilar, which is a much more sophisticated way of explaining why this is true. I mean, bisimilar potentialist systems always have the same truth assertions being made, and he proved that that's actually what's going on here. There's a bisimilarity. Okay. The L theory determines the diamond L theory. So if I'm in mod T, so the models of a first order theory, all algebraic plus fields or all groups, whatever. If I have an elementary substructure, which means that L assertions in M agree about individuals that have the same truth value either in M or N, then it's also elementary in the diamond L modal language. It's not true for L diamond. It can't be because of what we already said. Namely, I can express countably infinite, but I can have a countable graph that's elementary in an uncountable graph. That's exactly what the Leibniz-Bohm theorem gives us. But it wouldn't be L diamond elementary because this one would think I'm countable and this one would think I'm not countable. And that we proved it's expressible in the modal language, but it's not expressible in the diamond L language. You have to put modal operators under the scope of quantifiers to do those arguments. Okay, there's another lemma that if two structures have the same theory in the first order theory, then they also have the same diamond L. This is a consequence of this because two structures have the same theory just in case they have a common elementary extension. But that elementary extension would be a diamond L elementary extension of both of them, and so therefore they'd have to also have the same diamond L. It's not true for L diamond. Okay, every diamond L formula is equivalent to an infinitary assertion in the L language. You don't need any modalities if you're willing to go to infinitary logic. So here's the proof. Given a statement phi in the diamond L language, I look at the L theories of the models where phi is true. Okay. Phi bar is a first order theory of a model in which phi holds. Phi is a modal assertion, but T bar is just a first order theory. And then because the L theory determines the diamond L theory because of the previous lemma, if you know the L theory, you know the diamond L theory. Phi is just equivalent to saying I'm in one of the models that has an L theory in which phi holds. So it's saying this conjunction is saying that T bar holds. And this disjunction is saying T bar is one of the theories of a model in which phi holds. So basically this whole thing is an infinitary assertion saying you're living in a model that whose L theory is one of the theories in which phi is true in such a model. Okay, this is a countable conjunction if we're in a countable language. Well, actually, we can assume that because phi has only finitely many relation symbols in it or whatever. So we can assume the language countable anyway. So this becomes a countable conjunction. So it's almost L omega 1 omega, except not quite because this is a continuum size disjunction here, not a countable disjunction. So it's open whether we can do it in L omega 1 omega using only countable disjunctions and conjunctions. There's things to say about quantifier elimination. I want to keep track of the time. I don't know how much time. Is this the clock here? 4:02? Is that the current time?
Yes.
So we have like 20 minutes. Okay, I think I'm doing
bit
fine.
more.
Okay. So a theory admits to say that if you have a theory, it admits quantifier elimination when every assertion in the theory is equivalent to a quantifier-free assertion. That's what it means to admit elimination of quantifiers. And there's many theories that admit elimination of quantifiers, like theory of a dense linear order or real close fields, admit quantifier elimination. If you have one of those theories that admits quantifier elimination, then it also admits modality elimination. In the modal language, you can eliminate the modality. In fact, it admits modality trivialization. So the difference is that modality elimination means that every modal assertion is equivalent to a modality-free assertion. And modality trivialization means that happens just by dropping the modal operator. So possible phi is just equivalent to phi. Okay. These are not equivalent to each other. We have examples where a theory admits modality elimination, but not trivialization. But in fact, of course, when you have a theory that admits quantifier elimination, it means something very special about that theory. It's not capable of expressing as much maybe as you thought. So it's maybe not surprising that also with the modality you can't express. So, right. Okay, the following are equivalent. So if you have modality trivialization, that's where you can just drop the modality. That's just equivalent. It doesn't matter if it's L diamond or diamond L or L. Those in fact are all equivalent. And it's just equivalent to saying that T is model complete. And model complete means that submodels of the theory are automatically elementary submodels. Okay. So, right. So let's now talk about this actuality operator. So we want to augment the language with an actuality operator, which allows reference back to the actual world. So the idea is that we're living in some group or graph or whatever it is, model of set theory, and in the context of all these other ones, and we want to talk about whether things are possible or necessary or possibly necessary or possibly necessarily possible and things like that. But in those assertions, we want to refer back to what's actually true in that original place where we started. So for example, in graph theory, this statement here says possibly there's a point X such that everybody is connected to it if and only if it was actual, it was in the actual world, and also actually it had no neighbors. So this is saying it's possible to have a point which is connected to all and only the original actual points that were isolated. But obviously you can do that. If you have a graph and it's the actual world, then I can just add a new point which is pointing at all the isolated points. And I'm going to make this true. Okay, so there's more complicated versions of actuality where you can have like several actual worlds, and there's subscripts like actual 1, actual 2, and so on. You would say, well, actually in world 1, blah, blah, blah. Actually, world 2 thinks, blah, blah, blah. Okay. So there's these iterated semantics. They become quite complicated. It's related to the Bloch operators, if anyone is familiar with that. Okay, it appears to be stronger than modal graph theory. So it can express equinumerosity of neighbor sets. So if I have a graph and I have nodes X and Y, I might want to say their neighbor sets are equinumerous. And we don't know how to do that in the most general case. We don't know how to do that in modal graph theory. But if this world is counted as the actual world, then we can do it. The problem is that when you make a modal assertion and you say, well, possibly something, then you can't tell what the original graph was, because you're adding nodes and you don't know which ones are new and which ones are old. And actuality is exactly what enables you to tell that apart. Okay, we can express well-foundedness. With actuality, we can interpret the full set-theoretic universe in graph theory. So, for example, the continuum hypothesis, we can tell whether it's true or not by making an assertion about the finite cyclic graph of size phi in modal actual graph theory. Because we just say, well, I mean, it's going to be a complicated assertion that summons into existence this gigantic graph that codes the set-theoretic universe up to v sub omega plus 2 in such a way that we can tell whether or not CH holds there or not. And all of that is expressible as an assertion about that tiny little finite graph. So I think it's quite remarkable. Okay, so the question had remained, we didn't know the answer at first, is actuality expressive with modal graph theory? And until about a month ago, we didn't know the answer, but Wojciech and I finally figured it out. The answer is no. And this is one way of seeing it. Say, take account of the infinite graph. This continuum many subgraphs that might have arisen, that might have given rise to that graph. Any one of those subgraphs could have been actual, but only countably many of them are definable because the language is countable. So I can pick a subgraph which isn't definable in modal graph theory, and I'm going to think of that one as the actual world. But now I can define it because it's the actual world in that larger graph. So with actuality, I can define subsets that I couldn't define in modal graph theory, which is a kind of answer to this question, although it's not as robust of an answer as we would like, but it answers the question. Okay. So now a modal assertion. These are propositional variables, propositional atoms. We say it's valid. It's kind of like a template. It's valid if all the substitution instances of it where we put assertions in the allowed language in for those atoms, if all of those are true. Okay. So for example, maybe if I think of these p's as propositional variables, then these are substitution instances of box P implies box P. So it's really each one of these p's here, you know, okay, this p is not like those, these p's are like those. Each one of these modal assertions is like a scheme. It's a template for an infinite list of the substitution instances that would arise from it. Just like each one of these patterns is really an infinite scheme of statements, all having this form. Okay. So let me tell you a little bit. S4, which is axiomatized by these principles, is valid in every potentialist system. So this is expressing that the accessibility relation is reflexive. This one is expressing that the accessibility relation is transitive. This is just sort of the duality of possibility and necessity. S4.2, I'm sorry, the converse Barkin. So necessarily, if everybody has phi, then everybody necessarily has phi. And this is true whenever accessibility relation is inflationary on the domains. You only add individuals, you never remove individuals. So in modal theory, it's a potentialist theory in the sense that we never throw anybody away. We only get new people as we go. And then we're always going to get the converse Barkin in that. The Barkin is the other one, but the converse Barkin is what potentialism is about. Okay. If the potential system is convergent, which means that if you go to two other worlds, then you can bring them together. If it's convergent, then you get S4.2, which is the statement that if something is possibly necessary, then it's necessarily possible. And that's just because if it's possibly necessary, you can go to the world where all the later worlds think it's true. But then if you go somewhere else, because it was convergent, you could find a common extension, and therefore it must have been possible over here. So therefore, but that was arbitrary, so it's necessarily possible. If it's possibly necessary, it's necessarily possible. If you have amalgamation, which is just like convergence, except the diagram commutes, so this only makes sense in a case where we're not using direct extension. In direct extensions, convergence and amalgamation are the same thing, because it's the identity map inclusion both times. But if we're embedding, then I want to find a common extension. Sometimes you can do that without the diagram commuting, and then you still get S4.2. I'm sorry, you get S4.2 for sentences, but sometimes you can do it in such a way that the diagram commutes, and that's what it takes to handle parameters also, to get S4.2 with parameters. If some potential systems are linearly pre-ordered, so when given any two, one of them is embedding into the other or accessing the other. And in that case, you get S4.3. S4.3 is expressing linearity because it says if two things are possible, then it's possible that you have one of them while the other one remains possible. So if you think about sort of temporal logic, it means that one of them happens first. If two things happen in the future, then there's a time where one of them is true and the other one is still yet to be true. Or maybe also true at that point, because if something is true, it counts as possible because of reflexivity. Okay. So let's give some examples here. So a statement is called a switch if it's possible that it's true and it's possible that it's false. So for example, yesterday in my talk, I talked about the condition hypothesis as being a switch with respect to forcing, because you can force it and force the negation and force it and force the negation again as much as you want. Who can give me a switch in graph theory? If I want a statement in graph theory, so that any graph, you can make it true, and then you can make it false again in a bigger graph.
For connectivity.
Connectivity, okay, but that's not expressible in graph theory itself. So that's a modal graph theory assertion, which is fine, it's a switch, but maybe we can do a little bit better by having an L assertion. So just in the language of graph theory itself, I think a similar idea will work. Maybe that's what you meant anyway.
Size.
Oh, evenness of size, yeah, but that's not expressible in the, because once it's infinite, I guess they're all even then. So
Well, completeness, I guess.
no, but if it's not complete, it's never going to be complete because we don't add edges. We're just I'm thinking induced subgraph always. So if it's not,
You're thinking, okay.
yeah, I'm sorry. That's what I was always thinking induced. If you wanted subgraph in that sense where you're allowed also to add edges, then completeness would be an example because you can make it complete. You can just add all the edges you want and then go to a bigger graph where it's not complete. So that would be a switch in that sense of accessibility. If you're thinking like I was in like Wojciech and I did, where it was induced subgraph, you're not allowed to add new edges. But you can say diameter 2, because we already argued diameter 2 is always possible, but then you can add some isolated points that doesn't have diameter 2 anymore, and then make it diameter 2 again. So that's a switch. Okay. A button is a statement that's possibly necessary. So it's pushed if it's already necessary. You can see you push the button, you can't unpush it. A switch, you can turn it on and off. A button, once you push it, it's pushed. You can't unpush it. Okay, who can give me, in groups, can you give me a switch in groups? No, because once it's not abelian, it's necessarily not abelian. You can't turn that off, right? So being non-abelian is a button, Oh, right, because you can make it true, and once it's true, it's gonna be necessary. But I want to switch in groups. So I want a statement in the language of group theory, a first order language of group theory would be best, such that you can make it true in an extension of any group, you can make it true in an extension of that group, and then you can make it false again. In any group. So having a trivial center is an example. You can always add a point that's not in the center, doesn't commute with everybody. But you can always add a point that doesn't commute with anybody, makes the center trivial. So every group has an extension with a trivial center, and every group has an extension with a non-trivial center. So that's a switch, having a non-trivial center. It's expressible in the first order language of groups. Okay, being non-abelian is a button in groups, but what about graphs? Can we make a button in graphs? Under induced subgraph is what I'm always thinking, but a statement that you can make true over any graph is not necessarily true in every graph, but you can make it true, and once it's true, we want it to stay true. Infinite, but that's not expressible in the first order language of graphs. It is a button in the modal language. I mean, so that's definitely a button, but a better button would be in a more simply expressible one. Yes?
Would completeness?
Completeness is not a button because I can't, first of all, it's not even possible to make an incomplete graph complete if we're doing induced subgraph, but is your name Charlotte?
Yeah, that's right.
Charlotte's suggestion that we just look at the other notion of subgraph where it's allowed to add, then we can make it complete if we want, and then we can make it incomplete, and then we can make it complete again. So it's a switch and not a button.
So if you have a 3 cycle,
Right.
it's never going away.
Existence of a triangle or a 3 cycle. You have to say there's a triangle.
Right.
That's first order expressible, and once you have it, it's never gone away. And so therefore, there's a triangle or a pentagon, whatever you want. Okay, a ratchet is a sequence of buttons such that they only get more true. The ratchet is a one-way thing, right? It only gets more true. So each of them is, once it's true, it's necessary, and each of them implies all the previous ones. Right? So, okay. And a railway switch is a statement so that possibly necessary are, but also possibly necessary not are. So the idea is that you're standing at the switch, the train's coming. You can push it this way, so the train is going to go that way, it's going to stay there. Or you can pull it, the train is going to go on this track. Okay, so you can either make it necessarily true or you can make it necessarily false. Yeah. This is incompatible with convergence and amalgamation, because if you go to the place where R is necessary and you go to the place where not R is necessary, you can't have any common extension, right? So railway switches are totally incompatible with convergence and amalgamation. So we won't be able to give any such example in groups or graphs or so on. But we can if we make the theory a little bit better, like maybe the theory says in groups, the theory says, it's the theory of groups such that if there's an element of order 2, then there's no element of order 3. Okay. Maybe I don't have either orders yet. I could add an element of order 2. But once I have it, I'm never going to have an element of order 3. Okay, or I could add an element of order 3. And then I'm never going to have an element of order 2. So the statement would be, I guess, there is an element of order 2. So if the theory says, I'm talking about groups such that if there's an element of order 2, then there's no element of order 3. Then the statement, there is an element of order 2, is a railway switch, because you can make it, it's possibly necessarily true over the trivial group, but also its negation is possibly. Okay, and there's more complicated things, but I'm running out of time. So why don't I just tell you the key things. So the purpose of these kind of control statements allows you to make deductions about what the modal logic of the validities of that system is. So if you have independent switches, then the validities are contained in the modal theory S file. And if you have independent buttons and switches, so that's a arbitrarily large finite families of buttons and switches that can be controlled independently. So you can push any button without pushing any of the other buttons. And you can flip the switches without accidentally pushing any of the buttons. Okay, that's what it means to be independent. And in that situation, you get S4.2. And if you have long ratchets and switches, then it's contained in S4.3. And if you have round yards, then it's contained in S4, equal to S4. So this oftentimes algebraists or mathematicians who don't know any modal logic, but they understand their structures deeply, they can produce the control statements because they have a deep understanding of their subject matter. And this theorem is the kind of bridge between the subject matter experts and the modal logic validity. So I can just say, well, can you give me statements, that are independent buttons or that have this ratchet property? And if they can, then we can determine often what the modal logic is because of this theorem. So this is the purpose of these control statements way of thinking, is that it's often easy to come up with these statements. And in fact, that's how Benedict Loeb and I solved the modal logic of forcing. So we were looking at the models of set theory, and the accessibility relation was the forcing extension relation. And we proved that we produced buttons and switches, independent buttons and switches in that case. And we were able to show that the modal logic of forcing is exactly S4.2, and so on in many other potentially systems. So models of PA under end extension, we can produce railway switches. So the modal logic of that situation is exactly S4, and so on. In many other different cases, we were able to produce the switches and then invoke this theorem to get the validities. I think I'm out of time, so let me just tell you this one last thing. Okay, so if you have a countable graph, I claim it validates S5. S5 is this axiom: possibly necessary statements are already true. That's what S5 says. That's true if and only if it's the countable random graph, the Rado graph. And let me just convince you of that. The countable random graph is the countable graph it satisfies the finite pattern property, which means if I have two disjoint finite sets of vertices, A and B, then there's a vertex that's attached to everybody in A and to nobody in B. That's called the finite pattern property. For every disjoint finite A and B, there's a node attached to everybody in A with no edges to B. But that's an instance of S5. Any such instance of the pattern property, you're asking, is there a guy that's attached to these guys and not to those guys? But that's a possibly necessary statement, because if I didn't have one, I could just add a node in a bigger model. It's possible that I had such a node, and once I had it, it would be necessary that I'm fulfilling that property if I'm in the induced subgraph case. Then, therefore, every instance of the finite pattern property is a possibly necessary statement. And so if I'm validating S5, that means I have to satisfy the finite pattern property, which means I have to be the countable random graph because it's characterized. The countable random graph is characterized by that finite pattern property. And conversely, if G is already the countable random graph and it has a possibly necessary statement, that means there's some bigger graph where phi is necessary. But that bigger graph embeds inside the countable random graph because it's a universal graph for countable structures. So I can put that bigger graph where it was necessary inside the countable random graph and fixing the parameters. It's a very robust embedding universality property. And so I can view the countable random graph, the original one itself, as an extension of a graph that had the property that phi was necessary, and therefore phi is already true in the countable random graph. So I've argued that if you have a countable random graph with a possibly necessary statement, then in fact it has a subgraph where phi was already necessary, and so phi is true in the countable random graph already. I find that quite remarkable. A similar thing is true in fields where you get the being algebraically closed is the similar property. And then that's for countable graphs. If you're in the general case, then an arbitrary graph, including uncountable, satisfies S5 with parameters if and only if it satisfies the theory of the common random graph, which is just graph theory plus this finite pattern property, which is expressible. So then that's with parameters. If you just want it for sentences, then it's equivalent to just being universal for finite graphs. In other words, having a subgraph, having a copy of every finite graph as a subgraph. You could just put them next to each other. That's definitely not the common random graph, but it will satisfy S5 for sentences if you're not allowed to refer to individual points. Okay, so I guess I'm really out of time now. So let me just be done here. So thank you very much. Oops, there we go.